Hey folks, today we're going to go over the pwnable.kr level of collision. So we just did FD, so now we're going to look at collision. So collision is a 3-point problem. Does that mean it's 3 times as much, more difficult than the FD problem? I have absolutely no idea. These actually creating fair point systems for challenges is incredibly difficult. So hey, who knows? But we'll dive right in. So it says, Daddy told me something cool about MD5 hash collision today. Sounds interesting. I want to do something like that. So SSH call at pwnable.kr, port 2222, password guest. So let's go in. Bop. All right, well, SSH there. Normally I'd have to type the guest password in, but I have SSH multiplexing turned on here, so it's actually nice. It'll keep the connection open for me, and that's why it was so fast. So when we get here, same thing as before on the other one. So we have a flag file that we desperately want to access, but we cannot access it. It is permission denied. And so when we look call.c, so we have a C file, and we have the call binary, which is set UID of call underscore pwn, which is exactly the user we need to be able to read the flag. So I've already downloaded these to my local machine. Let's look at call.c. So we have this unsigned long hash code of 21DD09EC, a function called check password. That sounds interesting. A main function which takes in an argc and an argv vector and says if argc is less than 2, then print out the usage is argv0, then passcode. So we should be able to verify that this is the case. Yep, so we ran this binary. We got usage is equal to /call passcode. So we need to pass in a passcode to pass this. Next, the next check says if the string length of argv1 is not equal to 20, then the passcode length should be 20 bytes. So here we know, okay, we have to pass in something that's 20 bytes long. The next thing says call check password on argv1. Check if that's equal to hash code. If it is, then output system bin cat flag return 0. Otherwise, print out wrong passcode. Ugh, I hate C code that has this with the dangling clause here. Always use your curly braces. All right, even if it's only one line. All right, so we can try this. We can just put out 101, and we can see, passcode length should be 20 bytes. So we can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And it's like wrong passcode, which makes sense because we just typed in something random. But we know we got past this first check, and so it's now calling check password. So now let's dive into this check password function. So we can see it's a function that takes in a character pointer p, returns an unsigned long. So what does it do? It first casts our character pointer p to an integer pointer. So what this means is that it's going to still be pointed to the same memory location, but now when you dereference that, rather than talking about a single byte, which is a character, you'll actually be talking about 4 bytes. We have an int I, a result 0, and we're gonna loop from I from 0 to 5, I++. So we know this will execute 5 times. It will say result plus equals IP bracket I. So remember, the super important thing to remember about C code is that IP, so whenever you have a pointer, IP bracket I is exactly the same thing as IP plus I, which is pointer arithmetic, dereference. So these literally, the bracket notation is syntactical sugar for this exact thing here. So actually, I may need to make this smaller. Okay, so that should be good there. So what this is doing, so it's starting the result as 0, and it's adding up, and so it's incrementing over. So remember, we send 20 bytes. It's taking the first 4 bytes, interpreting them as an integer, adding that to result, and then summing those all up such that the final result has to be equal to the hash code, which is hex 21dd09EC. So one super easy way to think about this is thinking, okay, well, why not just send all zeros, right? So we can send, if we do something like, so the first thing is we have to remember, okay, we have to be inputting in here raw bytes. So let's do this. We're going to reset this. We're going to have this be our C code, and we will get in here. Okay, so if we execute this program, we need to execute raw bytes. So one thing is, hey, this is the number, this is our target number. So the first thing is, how do we get raw bytes into this program? I actually love using Python to do this. So you can use Python-C, which says, hey, don't execute a Python file, but execute the command right here so we can build a one-liner. So Python-C, what is the Python program we want to do? We want to print out. So let's first, we want XEC, X09, XDD, X21. So this is our target, right? This is what we want to be in this result variable here. So why did I flip these bytes around? That has to do with endianness. So you should go look up the difference between little endian and big endian. The idea is when you interpret 4 bytes, which byte of those 4 bytes is the most significant byte. So on little endian systems, it's backwards of the way you'd expect it. So this is just something you have to deal with and get used to. So even though this is what we want in the hash code, the string of bytes that we have in memory will have to be this way. This is something you just get used to from doing many and many of these challenges. So this is what we want. If we do this, this is not going to work. Why not? Well, A, we didn't input the program correctly, but B, it's going to tell us that it should be 20 bytes. Right? And we only put in 4 bytes, 1, 2, 3, 4. So we have to then say, okay, well, let's just append. So this is our final value. This is what we want to be. So why not just append, let's say 0, 0. So we want null bytes times, so we already have 4. We want 20. Let's do 16. And so it still says passcode length should be 20 bytes. So at this point, we have to wonder, what's wrong with this nonsense? Either something's wrong with the challenge or something's wrong with our understanding of how this challenge works. So actually for this, I think it'd be nice to drop into GDB. For GDB, I actually use this Jeff, GDB-GF extension, which is a nice, actually makes it a lot easier. So I'm gonna set a breakpoint on main, and I'm going to run it with this. So it's super cool. You can use, just run like this. And now when we get here, it's telling me it's at main. Here's GEF. So this thing is super cool. It's basically nice that it shows you, it has where you are in the code. So it automatically shows you where you are in the code. It automatically shows you where you are in the stack trace, the current stack, although I hate that it goes down. I always draw my stacks going up, but that may be something I'll fix later. And then here it shows us the value inside all the registers. So super, useful stuff here. So I'm right in the main function. Now I can step through this to kind of see about why it's going to, so why it's going to execute. So what did it just do? It is, so when we step through here, so it's going to call puts, and it's going to say password code length should be 20 bytes. So let's restart it back here. It should show us, hey, next instruction. So right before we got there, we compared that, and then we're going to do, I see. So it's, Yeah, so 14, hex 14 is going to be 20. I bet. There you go. And so it's comparing that value with 20, but what is it comparing? EDI. So if we go XS EDI, so the problem is if we look at the C code here, it's actually compiled our string length check into, I believe it's inline compiling that into this add repni, all this fun stuff here. But we can actually look because we know due to the argv, due to the calling convention, the cdecl calling convention, that main, the very first arguments of main will be at EBP. So at EBP plus 8 is the first argument of main. I want this to be wide. So we can actually see that okay, so the 3 is interesting. I'm not sure why it's 3, but that's okay. Oh, it checks if it's less than 2. Okay, we have 3 argv vectors. That's interesting, but let's see. So that means plus 8. So 3 is our argv pointer here, our argc value. This is going to be argc. This value here is going to be a pointer to an array of pointers of argv. So if we do x20y to x of, oops, that's not right, of this guy, that will give us a list of pointers. So this, if we're correct, this first one should give us, so now what I'm going to do is I'm going to use S and I'm going to tell it to interpret these as strings. Okay, that didn't work. So, okay, so let's do, go back here. We'll do this. So this very first string should be the string that we used, our argv0. Yeah, so this is perfect. So this is the path that GDB used to execute this binary. Awesome. So the second value then should be argv1. Interesting. Well, it's not a printable string. That makes sense. 20x. So how do we run this? EC, and then this problem is this 0,9. So this 0,9 is not being considered as a, so the string length here is going to be just 1. Probably because this 0,9 is probably white space. If we did man ASCII, we would see that the hex 0,9 is a horizontal tab. And so that may be what, actually that's a good question. Let's see, what is the byte sequence of, so this is our argv1, what's argv2? Because we didn't think to pass in 2 arguments, it's dd21. And if we go back to how we ran this, dd21. So super interesting stuff here. So the 0,9, we can't have any white space characters. Oh, you know what? We definitely can. We'll just have to restart this like this. And we'll print out our stack one more time. And we'll see now we have 2 arguments. So again, it comes back to single quotes here. So the idea is because we had spaces and tabs in there, the bash shell was interpreting that as wanting to pass multiple arguments to this function, but we want to prevent that so we can put everything in double quotes. So we do that, and then we do, this is going to be our argv1. Now we can, I think we can just print out string length of this. We can see that it's d4, interesting, xs. So now if we do that and we look at it, let's look at it as, that's our environment pointer. Okay, makes sense. So right, this is argc, this is argv, so we actually didn't print out argv yet. 20y to s. So yeah, so this is going to be argv1, this will be argv2. We look at this, and if we did this as if we print out the string length of this, it'll tell us we only have 4 bytes, which is very surprising. Why? Because it looks like we printed out 200 bytes. And so what actually happened here? Let's look at the bytes. W20X. So we can see we have EC09DD21, which is perfect. That's exactly what we want in there. But we have a 0. What happened? Well, when we ran this, right, we tried to add 16 zeros at the end. But how does string length and C-style strings indicate that it's the end of the string? By using a null byte. So in our input string, we can't have a null byte because then string length will not think that we have 20 bytes. So we have to make sure. So this means that our initial thing of what we wanted to do is not correct. All right, let's pause. Okay, so now that we know why we can't pass in zeros, now the idea is, okay, so what do we want to pass in? So we know we can get in the EC09DD21. So an easy thing to do would be, what about 01, 01, 01, 01, 01? Right, those would be the smallest, essentially the 01, 01, 01, 01, 01. So these would be the smallest. Oh, these are in base 10. That's why that doesn't make sense. Okay, 01, 01, 01, 01. So these are going to be the smallest values here. So if we do 4 of these, 4 sets of 4, this will be this times 4. Those will be added together for hex 04040404. And then finally the number that we want, which is going to be which will be 21DD09EC. So if we take 21DD09EC, subtract 01, 01, 01, 01 from it, we see 20DC08EB. So now if we, on our local copy, so now we understood why that one didn't work. Now we'll say, okay, let's do, it actually doesn't matter first or second or whatever because it's just being added together. Let's do X00, X01. Let's do 16 bytes of 01 followed by the string that we just put in. And we gotta remember we've got to swap the order. So this will be XEB, X08, XDC, X20. And we get length to be 20 bytes. Why? Because we forgot to double quote that guy. And it's telling us wrong passcode. So that is interesting. So let's take this plus 04, 04, 04, 04. That did not work. Okay, why did that not work? So we have 21DD09EC. Let's convert this to base 10 because I kind of don't trust. Go to our scratch here. And our other number is 04, 04, 04, 04. Which we don't want there, we want there, 04, 04, 04, 04. In base 16, so base 10, we'll copy this. And now let's do everything in base 10. So we will do this number subtracted by this number, switch it to base 10. So see, we get a different number here. So to be completely honest, I don't know exactly why this happened, but we can roll with it. So we'll get here. We need to print, so the number now is E8. We have to go back to front, remember, 05. D9, 1D. Boom. And that's when we get the bin cat flag no such file directory. Remember, because I'm running this locally. So if we take this command, pop it on over to the server, which is being slow. And I'm going to paste this command. So now we're going to execute this. We're going to call Python. We're going to pass that in, and hopefully we will pass the hashcode check. So let's see if this is the case. Hit enter, and we wait. And there we go. We get daddy. I just managed to create a hash collision. So we copy, paste that in. And of course, this is a little bit of a joke. So now we can actually see when we go back here that this cool MD5 hash collision is actually a bit of a lie. That doesn't actually mean anything. So it's not an MD5 hash collision, but it is, you could think of it as they're using a hash. They're using addition essentially as a hash. So we can do that, and it should tell us that yes, we are correct. It may not do it. I don't know, I've already solved this. So anyways, that's it. There we go. We already authenticated this flag. So thanks. Bye. Keep on hacking.